It's great to be with you today, and as we talk about simplifying radicals. If you want to open up your binders, we'll take a look at this, and we're going to review a couple concepts on exponents first, and then our main focus today will be on simplifying radicals. The first key idea that we're going to be looking at is just reviewing the idea of when you're multiplying two variables together, you're going to add the exponent. And just very simply, as an example of this, when we have x cubed times x to the fifth, that's going to be x to the 3 plus 5. And so that's going to simplify to x to the eighth. Nothing fancy. Realize you have 3 x's here, and then you have 5 x's next, and all told, that's going to be 8 x's. And so I just want you to realize that that is one of our factors as we're going through. The second piece that sometimes we have a little bit of an issue with is when you are multiplying two different numbers you add, like we did on the first one of the x to the eighth. But however, if you have a power to a power, and why don't you write that down here, a power raised to a power. If that happens, then you're going to multiply your exponents. So in this case, we have the 2 and the 3 of a power to a power. That's the first part, not to be predicated, though, by distributing that 3 to both parts on the inside. So we're going to have 3 cubed times x squared cubed. Now, you know 3 cubed means 3 times 3 times 3, so that's 27. But x squared cubed, that means x squared times x squared times x squared. And so that equals x to the sixth. The shortcut to that is by raising it and multiplying it to a power. So that's just a little review as we're looking at that. Now we want to review our perfect squares. And up on the board, we've often had our perfect squares. And let's just kind of go through these because we want to make sure that we're comfortable. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 is 25, and 6 is 36. Now, you all know those, but that's not a big deal at all. But what I want to reflect over then to the right is talk about 11 squared. 11 squared, just like 1 squared, ends in a 1. And so 11 squared is 121. 12 squared is very similar to 4. It ends in a 4. So 12 squared is 144. 13 squared ends in a 9, just like 3 does, and so it's 169. 14 squared ends in a 6, and it's 196, and it's the reverse of 169, being 196. 15 squared ends in a 5, and anything that's 5 squared ends in a 25, and so in this case, it's 225. 16 squared, just like 6 squared, ends in a 6, and that's 256. So that takes us through the first 6. Let's look at our bottom 4 of each side. 7 squared, as you know, is 49, then 64, then 81, and then 100. I think it's safe to say that you would understand that 17 squared is going to end in a 9, and that's 289. 18 squared ends in a 4, and that's 324. 19 squared ends just like 81 does in a 1, and it's 361. And 20 squared, just like 100, ends in a 0, and as you can very well imagine, it's 400. It's going to be important for us to know these perfect squares as we're working through. I'd suggest you take some time to memorize them, maybe make them as flashcards, but we need to really put these to memory like we had in algebra a year ago. Let's now look at our main idea for today, which is simplifying radicals. There's 2 methods to simplifying radicals in both of these cases. One of them is to break our radicals down into prime factors. For example, 8 is 2 times 2 times 2. What we can do is we can look at this and we can say, hey, there is 2 pairs of 2's. As a result, those 2 2's are going to come out, and the square root of 4 is 2 with a leftover radical 2 inside. Another way to look at this is we can break down 8 into a perfect square. Then we multiply that by what's left over. And the reason I'm writing this out is because it's what we're going to do each different time. So our perfect square that goes into 8 is 4, and what's left over is 2. The square root of 4 is 2. Left over is 2 as well. Let's look at our next example. Square root of 98. Over to the side, I'm going to write down my perfect squares. 2 squared is 4, 3 squared is 9, 4 squared is 16, 25, 36, 49, 64, 81, and 100. In many cases, that will be enough. We're going to say 98 falls right here. Now we're going to work backwards up the line, and we're going to say, does 81 or 64 or 49 go into 98? Well, actually 49 does. So we're going to carry down the 2, and we're going to break this into a perfect square times what's left over. 49 and 2. From there, square root of 49 is 7. And so 2 times 7 is 14 on the outside. On the other side, over here on the left, we're going to take this 98 and we're going to say, hey, that's 2 times 7 times 7. I'm now going to identify my pair of factors, which are my 2 7s, and they're going to come out as 1 7, leaving me with the same answer of 14 square root of 2. When we look at and compare this with variables, it's a little bit different. But with variables, what we're going to do is we're going to break down our x to the 6th into 6 x's multiplied together. Now I'm going to look at those 6 x's and say there's one pair, there's another pair, and there's a third pair. Each one of those pairs comes out as 1x. So I have x cubed coming out of my factors. When I look at this in terms of perfect squares, in terms of variables, your perfect squares are x squared, x to the 4th, x to the 6th, x to the 8th, x to the 10th, and so on. And the square root of each one of these is going to be the pairs that come out of it. So the square root of x squared is x. The square root of x to the 4th is x squared. The square root of x to the 6th is x cubed. The square root of x to the 8th is x to the 4th. And the square root of x to the 10th is x to the 5th. I think by now you see the pattern that you cut the exponent in half. I think I'm going to highlight that because that is a very important idea for what we're talking about here today. So as we look back at our square root of x to the 6th, 6 divided by 2 is 3, and that gives us x to the 3rd. It's a much faster approach to do than writing it out in expanded form, but the expanded form does work very effectively. Our example D, we have a multiple problem in each one. We actually have 3 pieces, the 75, x to the 5th, and y to the 4th. So over here on the left, I'm going to write this in expanded form. 75 is 3 times 25, and 25 is 5 times 5. I now have 5 x's and 4 y's. I'm going to circle my pairs. There's a pair of 5's, a pair of x's, another pair of x's, a pair of y's, and a pair of y's. Each one of these pairs is going to come out front singularly. So the 5 comes out, x squared comes out because we have 2 x's, and y squared comes out as well. What's left over? Well, anything that we haven't circled is what's left over. We have a 3 left over and 1 x left over, and so that's our answer. It's a very long process, though, on that first line. Let me show you a little bit different approach as we write this as a perfect square and what's left over. The perfect square that goes into 75 is 25, and 25 times 3 is 75. X to the 5th, what we're going to do is we're going to write the even number directly below 5, which is x to the 4th. Because if you remember, up here at the top, x to the 4th is a perfect square. After we take an x to the 4th out, we have 1x left over, because 1 plus 4 is 5. Y to the 4th is a perfect square because it's an even number. We now take out and simplify our radical. That's 5, cut the 4 in half, x squared, cut the y to the 4th in half, y squared, and what's left over is the 3x. I'm not going to write the exponent of 1, but we are going to take into account the fact that it is a 1 there, but it's still invisible. That kind of concludes our general overview here, and our homework today is going to be the worksheet of radical reviews. I'm going to record a second video of the examples of that worksheet that you might be able to look at if you get stuck on any of the problems.